Good evening to everyone. So this is the 12th lecture in the serial of Vijnana Ganga. And first lecture was delivered by Sanjay Dhurandhar from Ayuka. And the 12th lecture, Professor Padmanabhan, you are also from Ayuka. Again next month, that means second year's first lecture is also from Ayuka. Dr. Jain Narlikar will deliver that particular lecture. So we have been inviting professors from Ayuka, from TIFR, Institute of Science. Likewise, what Mr. Sharad Kale describes it, hardcore scientists. They should be seen by others. In Marathi poetry, it has been said by one of the poets that how the poet looks like should be seen by others. Kavito dise kasa anani. So this is our effort that scientists should be exhibited and he should be seen, and what they are contributing to the country is to be witnessed by us, whether we understand fully or not. But the attempt should be to understand. Well, Professor Padmanabhan today is going to deliver a lecture on understanding our universe, status and prospects. Briefly, Professor Thanu Padmanabhan, distinguished professor at Ayuka, Pune, is a renowned theoretical physicist who has authored about 270 research papers and 11 books, including 8 graduate level textbooks published by the Cambridge University Press. This is one of the rare things, Padmanabhan, that you have been writing the textbooks also. And so to understand Professor Padmanabhan should not be difficult. His research providing an alternative perspective of gravity, in which gravity arises as an emergent phenomenon, has far-reaching implications for quantum gravity and has won prizes 6 times from the Gravity Research Foundation USA, including the first award in 2008. In recognition of his achievements, the President of India awarded him Padma Shri in 2007. He is elected Fellow of the Third World Academy of Sciences and all the 3 academies of science in India. He was the President of the Cosmology Commission of the International Astronomical Union 2009-12, Chairman of the Astrophysics Physicists Commission of International Union of Pure and Applied Physics 2011-14, and a Sackler Distinguished Astronomer of the Institute of Astronomy, Cambridge. The national and international awards received by him include inaugural Infosys Prize in Physics Sciences 2009. And Infosys committee says that one who wins the Infosys award is a medal for Nobel Prize. Third World Academy of Sciences Prize in Physics 2011, Shanti Swarup Bhatnagar Award 1996, INSA Vishnu Bapu Medal 2007, Millennium Medal 2000, A.L. Kwasmi International Award 2002, Homi Bhabha Fellowship 2003, J.C. Bose Fellowship 2008, G.D. Birla Award for Scientific Research 2003, Meghnad Award of Melbourne University 2004, Goel Prize in Physical Sciences 2012-13, Birla Science Prize 1991, and INSA Young Scientist Award in 1984. And after receiving this paper, I do not know how many you have received. Thank you. This time we have a change. Instead of bouquet of flowers, we are going to give the fruits. And that shows that this is the 12th lecture, so we are matured enough.
Let me begin by thanking the organizers for giving me this opportunity to be here. This is my first visit to this organization, and I hope to come again, and I had wonderful hospitality from them. So the topic which I want to talk about is how do we understand the universe today from a point of view of a cosmologist or a physicist. And I was also told that we should highlight what is the Indian contribution to that, which will be strewn all across the talk. Okay, I'm not going to specifically point that out. Now, there are some questions about the universe which has made people wonder right from prehistory. So, the first question, of course, is what is the universe made of? And how does this universe evolve? And the most important of all questions, where did all this come from? How did this universe get started? Do we need some extra physical hypotheses for that? Or can we understand it from mathematics and physics? So, these are the questions everyone has talked about. And from that point of view, cosmology happens to be the youngest of all sciences. Sometimes people say cosmology is the oldest of all sciences because the men who was building pyramids were looking at the skies and were studying the stars, but that is not real study. Cosmology, a science, is defined by observations. Theoretical speculations and philosophy has no role in science. There has to be observations like in nuclear physics, condensed matter physics, or low temperature physics, and cosmology today is at par with nuclear physics, condensed matter physics, or any kind of other laboratory physics, except that our laboratory is the universe. And this observational ideas about the universe, nailing it down, what exactly it is, started around 1990. It is about 20 years old. So it is just reaching adulthood of 21 around this time. It is driven entirely by observational research. So this is the point I want to emphasize throughout the talk, so let me start with it. Don't think cosmology is speculation, cosmology is philosophy. You can sit in an armchair and think about it and say something about the universe. Sure, you can say a lot about the universe, all of which will be wrong. Okay. Today, we theoreticians are finding it very hard to explain the observations. Theoreticians are lagging behind, and that is why it is a challenging place. There are open questions, and questions which can be addressed, and questions which can be tested. So this is what is happening. Why is this so? The simple reason is that cosmology is one science where you can see the past, in some sense like geology, but cosmology is a really good example. When I am looking at any one of you, I am not seeing you as you are now, but I am seeing you as you were a few nanoseconds before, because the light takes a certain amount of time to come from there to here. When I am looking at the sun, I am not seeing the sun as it is now, I am seeing it as it was 8 minutes earlier. So the further you look, the earlier a phase in the cosmos you are directly observing. So what the universe was doing when it was 10 times smaller in size, I am assuming all of you know that universe is expanding. So 10 times smaller in size or 1000 times smaller in size, you don't have to speculate. You just look at an object which is sufficiently far away that its age coincides with the age of the universe when it was 10 times smaller in size. You ask the universe, it will tell you what it was. The only problem is that when you start looking at further and further, sources become dimmer and dimmer and you can't catch it. So that is why we had to wait till 1990 to start the science of cosmology. Technology improved tremendously. Our telescopes become very powerful and we could see very far. And that is what nailed it down. So I couldn't have given this talk 25 years back. One would have given philosophical speculations. So this is, as I said, this is no longer an armchair subject. These are all the various observatories which is pouring data into us in different wavebands in electromagnetic spectrum about the cosmos. Most of these are international observatories, and there are a few from India. GMRT is near Pune, and AstroSat, in case you missed it in the news items, is a completely indigenous satellite-based observatory. So this is on time when ISRO launched a satellite without any practical use. Okay, no communication, nothing which you can do on the ground, etc. It is purely esoteric purpose where it has astronomical instruments which will look at. And the instruments were built by a large collaboration of Indian scientists, totally indigenous, and that is taking data beautifully, and there are papers coming out of it. And GMRT is, of course, it is still probably the best radio telescope in the entire world in these wavebands. It's going to be superseded by some SCA in a decade or so, but right now we are leading the thing. And then there are, of course, several international discs. So cosmologists do something like this. It's pretty simple. Okay? So every day you go up in the morning and you fill these things and work these things out and see whether it makes sense. So what exactly is he doing? He is trying to build a bridge between two things. One is he or she is doing is that there is a structure of physical laws and there is a structure of the universe, and you want to link these two. Now you can link it in two ways. You can start from the physical laws and try to explain the structure of the universe. So you take known physical laws, and we don't know all the laws of physics. You take the known physical laws and you try to explain. This program has been brilliantly successful. We do understand the universe pretty well. Understand in the sense that you make a prediction, test it against observation, it matches. It matches to umpteen decimal places. This we have been able to do from a billionth of the second in the age of the universe to about 14 billion years, which is the current age. So by any stretch of imagination, this is a fantastic achievement which has come about. But this is not really the exciting thing. The really exciting thing is to use the structure of the universe and start probing before the 1 billionth of the second. That is, you go into the unknown realms of physical theories and see whether these physical theories, speculations can be tested by cosmology. Because some of these physical theories cannot be tested anywhere else. We don't have sufficiently high energy devices. So it will be a good idea to test this out. And it turns out that this is also has been very successful. That is why many of us are working on that. And as I said, this is intellectually more challenging. And that is what I will be concentrating on most of it. But before I do that, I have to explain to you both these. What are the structure of the physical laws and what is the structure of the universe? So I'm going to assume that the audience is not entirely physics based. So some of you will find it a little below your level. But what I'm going to do is I'm also going to throw in a few equations, which is intended for those guys and who can grasp that. And the rest of the audience can simply ignore the equations and everything will make sense to them. Okay. So in order to understand the structure of physical laws, you start with three things, which you would have heard of. One is Newtonian gravity, the Newton's law of gravity. The other is special theory of relativity, which is the brainchild of Einstein. And then there is something called quantum theory. Quantum theory is the physics of very small objects, like electrons, protons, neutrons, etc. And the theory which describes that is called the quantum theory. Now, what you can do is to start from Newtonian gravity. And Newtonian gravity rules over the macro world. I mean, if you take the planets which are going around the sun which is going around the galaxy, all the dynamics of the large scale structure, etc. is all covered by the Newtonian gravity. Let us go to special relativity. Now, special relativity, even if you don't know anything, you or your son has or a daughter has a t-shirt with E equals mc square. Okay? E equals mc square everybody knows. They may not know what each of the symbols mean and why 2 is put slightly up, etc. But that is one result which everybody knows. So he essentially said energy and mass are the same. More importantly, he said that you can combine space and time and combine it into space-time. So until that time, we used to think that time was absolute. What Einstein showed was that the flow of time gets affected by physical processes. Firstly, it gets affected by motion. Second, it gets affected by gravity. And because of which the space and time has to be talked together as a structure called space-time. So the third one is what I said is the quantum theory. That came from so many people. Unlike somebody like Einstein, you can identify one single guy and say that he produced quantum mechanics. To a great extent, Heisenberg is a good example. Now, the key idea, and this is what you use, it rules over the micro world, and if you want to study protons, neutrons, electrons, etc., you need quantum theory. And the most important idea from quantum theory was something called uncertainty principle. So if I take this and throw it, you know exactly what trajectory it will follow and where it will hit. How do I know the trajectory? In order to know the trajectory, you need to know where it was and how fast you are moving. Then you know where it will be in the next moment. This is what we should be doing while driving, but not in Bombay. But in general, if you know where somebody is and with what speed he is moving, you should know where he will be, and you preferably try to avoid that point. So the trajectory can be defined only if you can measure where a person is and how fast it is moving. And generally, in physics, we assume that you can measure both of them. What Heisenberg told us that you can't do that. If you have an electron and you try to measure where it is, that measurement will disturb its speed so that you don't know what speed it is moving. So you cannot measure certain variables simultaneously, and this is called the uncertainty principle. Now if we will start combining these two, so I said I have explained all the three of these, and if you combine special relativity with Newtonian gravity, you end up getting what is known as general theory of relativity. Now this general theory of relativity describes this Newtonian gravity in a different language. It describes it as a curvature of space-time. So it is like, think of this as a mattress, and I have put a ball here. So the mattress gets curved because of the ball, let us say. Now if you put another ball here, because of the curvature, that ball is going to roll down to it. If you didn't know there was a mattress, you will say that this big ball is attracting this small ball. So the gravitational attraction between two bodies is essentially a phenomena coming from the curvature of the underlying space-time. And he also wrote down a formula for that, and this is actually exact. What he said was, if there is some amount of energy density, remember E equals mc square, mass is same as energy. So if there is some amount of energy per unit volume, the curvature it produces will be very large if the energy is very large. Here it is defined in terms of what is known as a radius of curvature. So if I take this object and curve it, if I curve it tremendously, then I can fit a small circle here. If I curve it slightly, I fit a very large circle here. So the radius of the circle is large when the curvature is small, and vice versa. And that is what this 1 by tells you. In particular, if the density is constant, then the curvature will be constant, etc. So we have done this. Newtonian gravity and special relativity combined gives you the general theory of relativity, where space-time is described as a curved manifold is the technical term. Essentially it is a mattress with a ball on it. Think of it like that. Now I want to know what happens when you combine special relativity with quantum theory. Then you end up getting something called quantum field theory. Now the basic idea of quantum field theory is that what you thought was nothing, the vacuum where nothing is present, is no longer nothing. But in that vacuum, there is a constant production and annihilation of particles and antiparticles. So to every particle there is an antiparticle, like electron has an antiparticle called positron. In normal textbooks you study about electron, neutron and proton. You don't study about the antiparticles, but each one of them has an antiparticle. Electron has a positron. Now when you use terms like antiparticle, you again think it is some philosophical object, etc., etc. Nothing of that kind. If you go to a super specialty hospital, they will do something called PET. The PET scan, the P stands for positron. It is a positron emission tomography. So positrons, which was considered esoteric object once upon a time, is now being used in every super specialty hospital. They are producing positron, they are producing antiparticles. Okay? So this is something beautiful, because when theoreticians come up with this concept, it looks so esoteric and completely devoid of practical application, and then some very smart engineer thinks of a good application for it, and then it actually serves humanity in one form. So the vacuum fluctuations was the key idea. This and antiparticles were the key idea which comes from quantum field theory. Remember each one of these pillars, because the later structures are going to depend on this. So the vacuum is not an empty space, but there is this fluctuation. Fine. Now what do we need to do? Okay, we have combined all this. So you take this general relativity and you take this quantum field theory and you combine, and then you get something called quantum gravity. Except that you don't, because we don't know how to do that. So this is the last important frontier. I don't have a photograph to put there, and it is needed in cosmology. This is something which everybody knew, because in order to do cosmology, in order to understand where the universe came from, all the important questions below this 1 billionth of the second, you need a quantum theory of gravity. It can also be tested by cosmology. That is the good news. It is needed by cosmology. So if you have a model for quantum gravity, you go and ask what predictions it makes in cosmology. If the predictions agree with observation, you are on the right track. So this is the synthesis of microscopic physics with macroscopic physics. And that will be the sort of running theme when I am talking about it. Having described in a sort of very rapid way the structure of physical laws, let me talk about the structure of the universe, because the whole idea was to build a bridge between these two. Structure of the universe is relatively simple because it is just based on observations. So this is a picture of the sky. You have sun here, and this is the Proxima Centauri, Alpha Centauri, which is the nearest star. Then almost all these are stars, and many of you who are, if there are star watchers, they will recognize these names. Like for example, Sirius is here, which is the brightest star in the heavens, and the length scale is like 10 light years. 10 light years is what we are sampling. Now you go further. You go much further. Now this itself is 1000 light years. Then you still find stars, but you find the stars are in some kind of bands like this, with dark spaces in between. And you can again recognize stars. Here is Betelgeuse, which is the Arudra in Indian name. And this is the Orion belt. And some of you might know how to recognize these things in the sky. But you see these bands. Why do you see these bands? Do you see these bands because this is all part of a big galaxy called Milky Way galaxy in which we reside. So all the stars you see in the sky are the stars in our galaxy. And there are about 100 billion such stars in our galaxy, and sun is just one of them, and that sun just goes around here. And these spiral arms are named by various constellations. These are called the various spiral arms like Perseus arm, Cygnus arm, etc. of our Milky Way galaxy. This is the Milky Way galaxy. We have now gone to something like 10,000 light years size here. What happens if you go still further? The universe is essentially built out of galaxies. Just like if you take a material body, it is built out of atoms. You often don't worry about what is inside the atom when you study a material body. In the same sort of way, when you study about the very large scale structure of the universe, you don't worry what is inside a galaxy. You build it out of galaxies. So here is our Milky Way galaxy, and the next nearest large galaxy is something called Andromeda galaxy. Just barely visible to naked eye in a clear night, in a clear place, not in Bombay, not even in Pune nowadays. And, but with binoculars you can see this. This is the biggest galaxy. And all these dots which we have put are all galaxies. And they are all orbiting around these two big galaxies. So now the galaxies themselves are acting like planets. Okay, we have come away from that. This is an actual photograph. Up to this was sort of reproduction based on data. This is an actual photograph of Andromeda galaxy. And we have such photographs of thousands of galaxies. And this is just a zoo of galaxies. They come in all sizes and shapes, and telescopes can pick up data on that, and we can study them very, very precisely. If you will go to still larger scales, now this is like 100 million light years is just this line. You find that the galaxies are also distributed in some kind of filamentary shape with large voids in between. So this is very interesting. Galaxies are not distributed randomly. There is a pattern. There are filaments and sheets and all that. At the same time, they are not distributed very regularly. It is not like a lattice. So it is somewhere in between, and a cosmologist has to explain how it got this way. Why exactly galaxies are distributed this way? This is one question which we can ask and we can answer. We know how it is happening, and this is the shape of our universe. Now, this is one thing which I want to drive home. Normally, when you look at the sky, you see the stars and you find it fantastic. And all the poets have written about stars in one poetry or the other. That's because poets don't have eyes for galaxies. If only you can see galaxies, this is how your sky will look. Okay? This is actual photographs. This is flat projection of all the galaxies in the sky. It's so dense, it is so densely populated. And you can still feel these filamentary and these sizes, and the color coding is depending on its intensity and properties. These are put together by the work of several astronomers, mosaic by mosaic, and put together. That is why you have these things where there is no data. So this is actual data, and this is how there's over 1 million galaxies in the sky, which this is how sky will look. It would have been very beautiful. Unfortunately, we can't see it. Now let us ask, how are all these galaxies behaving? So there I would just like to introduce to you what I would call the discovery of the 20th century. If you talk to professors in other subjects, they will differ, but believe me, this is the discovery of the 20th century. It says that the entire universe is expanding. Okay. So that is rather strange, right? I mean, in fact, it is ridiculous because if you have a balloon and you blow air into it, it expands. It expands because there is space outside. Balloon is not everything, but universe is everything. So universe cannot expand into anything. So this is a completely wrong way of saying, but everybody says it like that and people read like that, so I am using that phrase. What you actually mean is that the distance between any two galaxies separated by a large distance is increasing. That is a very precise statement. Take any two galaxies sufficiently far away, the distance between them you measure today and measure tomorrow, it would have increased. So another way of thinking about this is like an infinite rubber sheet. So this is a rubber sheet in which they have grids, and these are galaxies in this rubber sheet. Now suppose two guys are stretching the rubber sheet this way and two guys are stretching the rubber sheet this way, and they are stretching it at very far away. So it is an infinite rubber sheet. There is no region which is not a rubber sheet, and the rubber sheet is going into non-rubber sheet area. Okay, it is the entire universe is a rubber sheet. Now when you expand, this is what will happen. The grid will expand and the distance between any two points will expand. So this is exactly what is happening in the universe, and it is expanding in this form. All the galaxies are moving away from each other. What is driving this expansion is actually Einstein's theory. I told you that the Einstein, now is when I am connecting up the cosmological part with the laws of physics part. The Einstein's theory described, John's theory of relativity described the gravity in a particular way, and it is described, this is the engine which drives the expansion of the universe. So these are the Einstein's equations written in tensorial form, and these equations explain to you how the universe is expanding. So we can understand it using that. Basically, the rule turns out to be extremely simple. If the radius of curvature is something, the universe doubles its size when in a time scale radius of curvature divided by speed of light. So you take the radius of curvature, ask how long it is going to take for light to go from the travel that radius of curvature. In that time scale, the size of the universe would have expanded. So of course, the radius of curvature is related to the energy density. When the universe expands, energy density should, any decent energy density should come down. Because it comes down, the radius of curvature will increase, therefore the doubling time will increase. Therefore, the expansion of the universe has to slow down. So it expands, but the expansion rate has to come down little by little. Keep this in mind, this will have implications in what follows. One more thing is that if the density is constant, you would have thought nothing is happening. That means the radius of curvature is a constant. No. If the radius of curvature is constant, it is going to double at that rate. This is like your national savings bond. It doubles every 7th year as a very rapid compound interest growth. Okay? That is exactly what the universe will do if the density remains constant. Normally, densities cannot remain constant when the universe expands. Densities has to drop. But if it remains constant for some reason, then it will go into a very aggressive expansion mode. This is another idea which comes from the theory, which will have practical implication. In addition to all this, the galaxies which is allowing us to understand the expansion of the universe, etc., there is also one more result which we have, which is the real smoking gun of this expansion of the universe. Suppose the universe is expanding. Then in the past it would have been smaller, denser, hotter, and there would have been a lot of radiation there. As the universe expands, this radiation would be cooling down and it has to be around us. This is the relic of a very hot phase. That has been seen. This was 1965, Nobel Prize was given to two people, Penzias and Wilson, for discovering what is known as cosmic microwave background radiation. Simply stated, imagine that you are sitting inside a microwave oven. The oven's temperature is kept at 2.73 Kelvin. And this is how the sky will look if you can see this radiation, and this is the radiation which is filling all around you. Now, this is as far as the radiation is concerned, but suppose you want to know what the material content of the universe is. Forget radiation. What about the real matter? What is the universe made of? This is again a question which people have pondered for such a long time. Today we know what it is. In order to measure this, cosmologists use a letter. This is the last letter of Greek alphabet called omega. It essentially arranged in such a way that it measures the relative rate of expansion and the strength of gravity. So imagine that the universe is like a ball which was thrown up. If I throw a ball up, gravity is pulling down and it has a speed with which it is going up. If the speed wins, it will never come back. If the gravity wins, it will go up to a maximum size and come back. And that is what most of the stones which we will be throwing will behave. But if you are throwing a rocket to escape from Earth's gravitational field, you will send it at a speed greater than what is called the escape velocity. When you do that, it will escape to eternity. So there is a critical parameter which you can write down, which is the escape speed divided by the strength of the gravity. In the same way, for the entire universe, there is the total amount of matter in the universe decides the gravity, and the rate at which the universe is expanding decides its kinetic energy. And the ratio between these two is defined by this omega. When you do this, you find that the omega equals 1 universe has a energy which is 0. It has positive kinetic energy and negative gravitational potential energy. The total energy of the universe, taking all the energies into account, will be 0 if omega is equal to 1. That is a critical value. If omega is greater than 1, gravity will dominate and the universe will go to a maximum size and will then recollapse. If omega is less than 1, the expansion will dominate and it will continue to expand forever. So the crucial question is, what is the omega for the universe? Omega equals 1 is a critical value, which is a sacred number. But we have to observe the universe, rather ask the universe what is its omega. We have to find that out from observation. When you do that, the first thing you can do is you take all the galaxies you see and you compute what its mass is. That we can do. We have powerful telescopes today, and then you divide it uniformly and ask what is the density. From that you can calculate the gravity and then you can compute omega. You do all that for everything which you can see and you get an omega of about 5%. So I am talking in percentages normalized to unity. So about 5% of the, if you want to have matter to just make the critical density universe, then all the visible matter you see only gives you 5%. Well, but is there anything which you have not seen, which you have missed out? Is there something to the universe which does not meet the eye? It turns out there is a lot. Not everything in the universe emits light. So the classic example of this is what is called a rotation curve. So here is a galaxy. Very fortunately, nature has provided us with tiny gaseous clouds here. These are like test particles. They don't contribute to the mass of the galaxy, but they go around the galaxy in the gravitational force of the galaxy. You can measure the speed with which it is moving. And from that you can calculate how much mass is there inside which is attracting it. So you can plot the speed and versus the distance from the center where the gas cloud is located, and with all these gas clouds you can compute what it should be. Theory predicts that it should go like this. That is, if there is only this visible matter which is there is nothing other than visible matter, the curve should go like this. You can see that observations tell you like this. So there is a lot more matter, there is a gap here, and this gap has to be filled by non-luminous matter, that is called dark matter. Okay. So this is, I have just shown you one graph. I mean, there are hundreds of galaxies in which the studies has been done, and every time you find that there is a dark matter, it is distributed around the galaxies. These galaxies are just floating in a halo of dark matter. And this dark matter is some kind of a particle, but it does not couple to electromagnetism, so it does not emit light. So, but there is nothing more esoteric than that in that. It is like any other elementary particle, but it does not couple to radiation. There are, for example, neutrinos, which does not couple to electromagnetic radiation. Unfortunately, neutrino would have been a lovely choice for dark matter, but it turns out that the numbers do not match. They do not contribute as much as they should. So there has to be some other heavier neutrino or some other quantity which has to contribute to this. This is another example of the dark matter. You see these arc-like structures here, and then there is a ring-like structure here. These highly distorted images. These are normal galaxies, like the nice round elliptical galaxies. But these galaxies, this galaxy for example, is very far away. Then there are nearby galaxies, anything which looks somewhat normal or nearby galaxies in a cluster. So the light from a very distant galaxy is coming through the gravitational field of the nearby galaxies. And the gravity affects the light, it bends it like a lens, and it also distorts it like a bad lens. So this is called a gravitational lens. And the amount of bending which it produces depends on amount of matter there. Whether the matter is luminous or non-luminous, I don't care. We use these galaxies as test. But the gravitation, whatever is here producing the gravity produces the distortion. And you can measure how much of dark matter is there. You do all that and you get around 25%, 24%, 25%. So you have 5% of visible matter, about 25% of dark matter, you have got up to 30%, that's it. So you are still not hitting the magic number 1. We will come back to it. We will come back to it a little later. But before that, let me address this question as to how did all these galaxies form? Okay. So I have been telling you about all these galaxies and I said that they have particular shape, size, distribution. How did it form? So the best way to do this is to make a universe and see whether we can do that. With today's powerful computers, you can actually make a universe in a laptop. I mean, at my times when I was a graduate student, we need a cluster. Okay. So this is the simulation of a universe. Each of these red dots are particles, they are moving under the laws of physics. And as time goes on, you find that rich get richer and poor gets poorer. The regions which had a slight over density has acquired, I will run it once again, has acquired more and more material, and the regions which had less density has lost out in the process. You can see regions which had higher density sort of indicated by yellow, which is condensing out. And that is the time running forward, billions of years, but in a computer you can do any of these things. And you simulate these, and finally you see that the kind of thing has the kind of voids and filamentary structures, etc. So people have done these sort of simulations and they find that things match extraordinarily well with observation. So we do know that these structures form because initially there were small perturbations and these perturbations grew to form structures like galaxies. But where did these perturbations come from? That is where the vacuum fluctuations I mentioned to you come into the thing. You cannot just say, it is turtles all the way. So you cannot sort of say that the galaxy today came up because there were some small fluctuations earlier on. Then the guy will ask, okay, where did that fluctuations come from? So somewhere along the line, you have to give the origin of these fluctuations. And this comes from the eternally present vacuum fluctuations of the very early universe, from which you can get these cosmic structures. But if you want to do this, you can do this in a computer, but if you want to really do this in the universe, you want to know whether it is consistent all the way through, whether everything which I have said is observationally testable. Fortunately, we can test this. How do we test this? I told you that there is this radiation which is at the temperature 2.73 Kelvin. Well, actually it is not strictly at 2.73 Kelvin. If you look very sharply, you will find that there are hot regions and cold regions in it. There is a tiny temperature difference between them. How tiny? Few parts in a million. It is that tiny. And that is why we couldn't detect it until 1992. 1992 is when this was detected. And these tiny wiggles are a goldmine of information. What does it tell you? It first vindicates the theory which I presented to you. I said that the galaxies today formed because there were small fluctuations in the universe. Are there small fluctuations in the universe? Ask the universe. Go and find out how the universe looked when the universe was 1,000 times smaller. This is the picture of the universe in the sky when the universe was 1,000 times smaller. This is direct observation. And that tells you that there are tiny fluctuations. These tiny fluctuations are what has, then you run it into the computer and ask whether these tiny fluctuations can actually produce the galaxies. That contains an interesting piece of physics which I will come to. But before that, I again have to pay homage to technology. The reason you cannot just speculate wildly about cosmology is because your speculations are bound to be wrong. This is what we had in 1992 when we first discovered these patches. We were very excited. We thought that we had got it, which is true, we got it. But then people went to Earth. 10 years later, this is the resolution you have. This is like some HD movie you are watching. And then this is the resolution we have in 2030. These are all satellite experiments designed to do this. And it is not going to improve much further in another 10 years. But we still are milking the data out of this. So these tiny, again, until and unless you actually measure these and you calculate things out of it, you cannot say anything about the universe. And that is what was done. So the picture now is that these vacuum fluctuations in the very early universe led to this, and that led to these cosmic structures today. So let us look at the first part. This first part works very well provided you have a phase of very rapid expansion in the very early universe. And the second part, which is due to this gravitational instability, depends on the nature and amount of matter in the universe. You tinker with the amount of matter, the kind of matter, you find that you don't get these structures, you get some other thing. So in order to get exactly the universe you are living in, this part tells you what kind of matter and contents you can have in the universe. When you do that, you are in for a great surprise. You find, first of all, the good news is that the omega total is precisely 1 to few parts in 1,000, and the atoms constitutes, atoms meaning the normal matter, visible matter, constitute about 4.6%, and the dark matter constitute 24%, I have told you this. The remaining part is not matter at all. It is effectively contributed by a term in Einstein's equation called the cosmological constant. Now this is the one which used to be called dark energy. Okay. So when you think of dark energy, there are two ways in which can be explained. When you think in terms of dark energy, you think in terms of a very esoteric matter which has negative pressure, very peculiar features, etc. Some of us were never comfortable with it. The other explanation is that it is just cosmological constant. It is just a term in the Einstein's equation. You have to modify the Einstein's equation. Now there is an issue with this cosmological constant which we have recently solved, and I will come back to that. So if you read about dark energy, that is essentially another term for cosmological constant. The cosmological constant can explain everything which the esoteric dark energy fluid can explain. Okay. So if this is true, can we test it again? Because as I said, there is no place for speculation. So if there is a cosmological constant, can we test it? Yes, indeed you can. It will turn out that the cosmological constant will accelerate the expansion of the universe. So the expansion rate of the universe today you can measure. You can also measure the expansion rate of the universe in the past. You just need powerful beacons from the past, and then you can measure anything about the past. When you do that, you can check whether it is accelerating or not. These beacons are called supernova. These are some very massive stars which go and explode in this form. It's an absolutely brilliant optical phenomena, and the one which is shown here is called the Crab Nebula, and this was recorded by Chinese astronomers. I'm sure all of you can read Chinese, and this is the recording of the supernova. I'm not frauding, because you can always Google it up and check whether I'm frauding. So the actual recorded observations of this supernova observation which Chinese have made, and this is around the peak of the Chola dynasty in South India. It happened on 4th of July in 1054. It's very amazing that we have no recorded evidence of this. Okay, and this is something which bothers many of us, and we are still looking for evidence, and we have to see whether it is there, etc., etc. The only passive explanation given is it must have been a very heavy monsoon, but I don't buy that. This object was visible to naked eye for 20 days, even during daytime. It was that bright, and it dimmed over 2 years' time, and many other civilizations have recorded it. Even Red Indians have recorded it. So it's a bit of a mystery which we need to get back to. So if you take these supernova observations, thousands of them, or okay, actually hundreds of them, and you put them together, this is what you get. This graph is from an work with, I have collaborated with somebody called Tirthankar Roy Chaudhary at NCRA. So again, an Indian contribution at some level. So this is all the supernova data plotted in a particular way, which we thought is the right way to plot it. Others were plotting it differently. What is plotted here is the speed of expansion of the universe, how fast the universe is expanding. This is the size of the universe. Today we are here. When you go into the past, and then you go still into the past, you can easily see that the speed of expansion is decreasing, reaches a minimum, and then increasing. Universe is accelerating here. This is what this data shows, and this is exactly what cosmological constant would do. So directly from these observations, showing it is decelerating and then it is accelerating, we can figure out that there is a cosmological constant in the universe or dark energy if you want a weird fluid, and you can measure its properties. Cosmological constant fits perfectly with this data. What it tells you is that if you actually plot the density of the universe against time, this is again observations, the density does not continuously decrease and go to 0. It reaches a plateau. There is a constant value at which the density of the universe stops. So there is a minimum density to the universe contributed by this cosmological constant. So what is this cosmological constant? So it is essentially a term in Einstein's equation which behaves like matter with negative pressure. We have never seen matter with negative pressure in the laboratory, so it is bad physics to invoke it. And all dark energy models invoke the matter with negative pressure. That is why it is very hard to understand. But the cosmological constant effectively provides that, but it is just a term in Einstein's equation. And it can drive the accelerated expansion of the universe at the present epoch. And this is what most people think is the most important puzzle in theoretical physics today. So let me try to explain to you what that puzzle is. So here is the cosmological constant, and for those of you who have some physics background, it has a dimension. It is like 1 pi length square, centimeter to the minus 2. Now there are 3 other constants we know in physics. This is the 4th one which has come in. One is Newton's constant, which comes from gravity. There is a h which comes from quantum theory, it is a Planck's constant, and c is the speed of light coming from relativity. These 3 together has dimensions of length square. So if you multiply it by lambda, you get a pure number. It is a dimensionless pure number. It could have been 0.32, it could have been pi by 2, it could have been some number. We can measure what it is, because observationally we know what this number is, and it's an extraordinarily tiny but non-zero number. It is written in mathematical notation. For those who do not follow this, this number is obtained by 1 by 1 followed by 123 zeros. Just think about it. 1 by 10 is a small number, 1 part in 10. Then 1 part in 100 is 1 divided by 1 with 2 zeros. Then you put 3 zeros, it is 1 in 1000. 4 zeros, it is 1 in 10,000. So you keep adding zeros in the denominator, put 123 zeros, it is that time. Of course, you don't measure it directly, but there are indirect measurements from which you can get its value. Theoretically, we don't know its value. This was a situation until a few years back. And that is why people were not very comfortable with this cosmological constant, because how can you have such a tiny number which is not zero? Okay, this was the question. Now, this is what many of us and our group, now I will come to things which we have been doing and our group has been spending time on, and we felt that we need a paradigm shift in our understanding of gravity itself. So the gravity, what we normally thought of as force and then as curvature of space-time, etc., could be what physicists call an emergent phenomenon. So that sounds like a pretty tough term, but let me try to explain to you what it is. You all know what emergent phenomena is. If you have an elastic band and you pull it, there is a theory of velocity which tells you with what force that rubber band will go back. If you have a bunch of gas particles and you heat it up, or even water, if you heat it up, you know how it is getting heated up, and there is a thermodynamic model which explains this. There is something called ideal gas law, which is at least some of you will recognize, which is the pressure into volume is proportional to the temperature. And these equations explain dynamics in a way which is reasonably independent of the microstructure. If I give you this law about a gas, you don't go and ask me, okay, what is the microscopic atomic constitution of that gas? Is it argon? Is it helium? Whether it is argon or helium, this law is valid. Okay? So for a very wide class of phenomena, like for example, if you are bending a metallic rod and it is oscillating as like a cantilever, an engineer will not ask what it is made of. He will ask you for the elastic properties of that material. These are given in terms of some numbers like Young's modulus, etc. If you give the strength of the material and a few things, he will know all the properties. A good engineer will never ask what is the protons and neutrons doing inside before talking about whether a bridge will be stable or not. So these are the emergent phenomena, and what we are finding is that the gravity is like the fluid mechanics of the atoms of space-time. So roughly speaking, the idea is like this. If you take the water in this bottle, it looks enormously smooth and continuous. It flows very smoothly. I can flow it, I can move my hand through it, etc. It is very smooth. But we know none of this is true. Water is made of molecules. It is made of molecules which are moving around rapidly. Most of the space inside the water is empty. There are atomic structure to water, but this is something which we cannot easily perceive. And the same thing happens to space. Space has its own atoms, and this atomic structure is not easy to perceive because these atoms are very tiny. So what we have to do is to study the atomic structure of matter, and this gas dynamics was done by the physicists before they knew the atomic structure of matter, and we want to study the gravity and space-time exactly the way they did that. So if you do this, that is, if you go around studying gravity as an effective phenomena, like a fluid mechanics, where the space is actually made of tiny atoms, again you will ask the question, how do I know space is made of atoms? In fact, this is the question people asked Boltzmann, the Austrian physicist, who first said that the water or any material is made of atoms, and the reason you can heat up water is because there are these tiny particles which can store it as their kinetic energy. So he said heat is a kind of a motion. It is somewhat surprising because we never teach history of physics even when we teach physics. And many of us have grown up with the atomic idea. It is surprising to know that atomic nature of matter, which we take so much for granted today, was not well accepted even in early 1900s. Early 1900 is when special theory of relativity is coming up. But there were people who were hesitant to accept it because you haven't seen it. So why do you want to postulate that there is a lot of empty space and tiny dots which are around? Maybe it is not right. We are in a similar situation today regarding the ideas which I am going to present now, which I have been doing in the last few slides, that the space itself is made of atoms of space. But we can't see it because it is so tiny. In 1 square centimeter, in a size of a stamp, there are 10 to the power 66. That is 1 followed by 66 zeros. That many atoms of space. This is much more than the real atoms in that stamp. Okay? But how can we test it? It turns out that you can actually test it in cosmology. The very tiny value of the tiny size of the atoms is compensated by the very large distances we have in cosmology. So the take-home message for you is a technical expression. So I will just explain it to those who are not familiar with numbers. I told you that in the very early universe, there was a phase of inflation where the universe was expanding very rapidly. That is characterized by some density, which is the rho inflation. Then in the normal phase, there is matter and radiation from which you can construct another density. Then I also told you that the cosmological constant contributes yet another density. There are 3 densities which are the signatures of our universe. So you can build a universe with any values for these 3. In the normal Einstein's theory, there is no relation between these 3 values. That is why we do not know what is the value of the cosmological constant. It is very tiny, but we don't know what it is. This approach which we have been developing actually tells you the numerical value of that. And this is the formula connecting it. And as I said, if you're not familiar with mathematics, you don't have to take the formula. But those who understand mathematics will see that it has a very small number here. Okay, it is exponential minus 36 pi square. And others will see that it has only numbers like 4, 27, 36, pi. Exponential is another mathematical symbol. There are no free parameters. Okay. So you take this theory, plug in the numbers, either this is true or it is false. And it turns out that it is remarkably true. So we believe that this is the right way forward, and this was one of the main results which our group has been delivering from this emergent gravity approach. That is, the gravity is an emergent phenomena idea. And it actually explains a deep puzzle in the case of the universe. Now, in the last few minutes of the talk, say 5 minutes or so, I want to talk about another question to which this approach will give an answer. It has not given the answer. We still have to work out the mathematics, and it is very complex, and we are working on that. But this is a question which is close to everybody's heart, so I want to spend at least some time. How did it all begin? Where did it all come from? Okay. Well, so you start with galaxies and subgalactic system. That is not a mystery at all. Again, because of observation. We actually see stars form. There are regions in the sky in our galaxy where today stars are being formed. It is condensing out of hot gas, it is collapsing, it is getting heated up. At some stage, the thermonuclear reaction set up, and that thermonuclear reaction is what we call sun or a star. And in fact, this thermonuclear reactions produce huge amount of elements, heavier elements. And when the stars explode as supernova, remember that supernova explosion I told you, it spills out all these elements into the interstellar space. Planets condense out of it. And that is where all these elementary particle things were made. Except for hydrogen and helium, which were made very early on. All other heavier elements, of which you and I are made, is coming out of a stellar explosion in the past. So we are all star children in that sense. So it is not too difficult to understand stellar evolution because there are so many of them, we can observe them. And I have also told you how galaxies got formed, right? So the point is that, yeah, this I will skip. Okay, so the real question is the cosmogenesis. So I have all these radiation and matter from which galaxies formed out, stars formed, planets formed, etc. But where did all this matter and the radiation came from? Okay, so you are just pushing the clock back. And how did the universe itself come into being? So many people believe that physics will never be able to answer this question. So do we have a phrase? I am not claiming that physics has answered the question. But the question to ask is, does physics has the mathematical foundation to be able to answer this question? The answer is yes, we can do that. It is based on the result that from the point of view of physics, universe is indistinguishable from the vacuum. So let me explain what the point of view of physics is. Physics tries to describe things in terms of what is known as conserved quantities. So let me explain that idea. So suppose I say that out of nothing, boom, the universe came out with all these matter and energy. Then you will say, hey, come on, you guys told me a few years back that energy is conserved. So how can nothing which has no energy give you a universe which has energy? But that is why I emphasize that the omega equals 1 universe has exactly 0 energy. If observations have told you that omega is 0.3 or 1.5, we are sunk. Okay? We could not have done it. But observations tell you that the omega is 1 to 1 part in 1000. And that is only limited by our observational techniques. When observations improve, it will give you 1, 1, 1 to arbitrary accuracy. So the universe has 0 energy, vacuum has 0 energy, universe can just be another manifestation of vacuum. Okay, let us look at something else. I said that the universe is expanding. Well, expansion is a motion where everything is moving like this. But can't the universe rotate? Why isn't the universe rotating? The huge structure, why is it not rotating? After all, it is moving forward. Why can't it rotate like this? It turns out that in physics, there is another conserved quantity called spin or the angular momentum. The vacuum has 0 spin. Vacuum does not have rotation. If the universe came out of vacuum, it cannot have rotation. So people have gone and tried to measure the rotation of the universe. If we can find even a tiny amount of rotation, again this model is sunk. But we haven't found any rotation. The universe just expands, but the rotation is bounded. I mean, the amount of rotation, you can never say something is 0 in physics. But keep measuring and it is smaller and smaller and smaller than what you are measuring. So there is no rotation. Another example, which may be familiar to at least a few people, is electric charge. So if you take electric charge is conserved. So if there is some amount of electric charge in the universe, vacuum does not have electric charge, and universe could not have evolved out of vacuum. The total electric charge in the universe happens to be 0. There are positive charge particles and negative charge particles. They balance each other so well to 1 part in some 10 to the 20. So in fact, probably it is even a better accuracy than that. I mean, to a very high accuracy, the total charge of the universe is 0. So what people have been trying to understand the cosmogenesis from is by what is called a vacuum instability. Now at this part it becomes technical. So if you have a vacuum state, I have convinced you that there is nothing in the laws of physics which prevents it from becoming the universe which we see. But that does not mean it should become the universe. Why doesn't it stay as a vacuum? Why did it become that? That has to do with an instability. So instability is a phenomena which people are usually familiar. If you try to tip a pencil on its point, it is unstable, it will fall. Mathematically, you can always balance the force and it should stay. But we know that it is an equilibrium, but it is an unstable equilibrium. So the vacuum, it turns out when you work out the mathematics, it turns out that the vacuum state is unstable equilibrium. And the stable state is where you have this expanding universe with omega equals 1. So just to sum up, what we do know is that the evolution of the universe from a fraction of a second to about 14 billion years is very well understood. It is understood observationally and theoretically. But in order to do that, the picture which emerges from it is that there were vacuum fluctuations which started from the very early universe, and that acted as the seeds to the cosmic structures which we see today. This you can demonstrate. And in order to do that, we need matter of a very weird composition, about 5% of normal visible matter, 24% of dark matter, and the rest contributed by the cosmological constant. And this is the one which is accelerating today's universe, and this is what people used to call the dark energy. The explanation for the value of the cosmological constant, in our opinion, might require yet another paradigm shift in gravity. We originally thought gravity was a force. Einstein came along and told us that gravity is the curvature of the space-time. Now we are suggesting that the space-time itself is made of atoms of space. And what you call gravity, the Einstein's theory, is just the fluid mechanics of these atoms. We had to go one step below and then study gravity at that level. And we have done it at a very preliminary level, and that already explains the value of the cosmological constant. And if you go still further, you may be able to explain even the greatest puzzles like cosmogenesis. Thank you very much. Yes, please.
How does the string theory fit into this?
Yeah, okay.
Also trying to combine the
That's right.
gravity and the quantum
Yeah.
explains everything.
Right. Now, personally, I believe string theory is a failure. It started in 1985, and it has been around. We have given them a very long rope. Many exciting mathematical results came up. Many exciting philosophical results came up. But physics-wise, it was a failure. They didn't come up with anything testable. So in that sense, many of these approaches which I am outlining came because of the frustration from string theory and loop quantum gravity not delivering the goods. So our approach was that the string, and I will tell you where it relates to. String theory in some sense starts from the minutest particles and tries to build it upwards. This approach starts from the top and goes down. So at some stage, these two things should meet. And these two things seems to meet in a concept called holography, which I didn't describe today. The approach which I described incorporates the concept of holography. Roughly speaking, holography tells you that if you have a region and you have a surface, what is going on in the region inside can be understood by what is going on in the surface. That turns out to be part of this approach as well. And that is the only connection we have. But where we score is that we have a direct, measurable observation which is testable by the cosmic results. Such a number or such a relation has not been given by any other models of quantum gravity. So we believe this is the right way to go. And string theory and other approaches to quantum gravity in rough sense still thought of space-time curvature and then say that, yeah, it is space-time curvature, but still gravity is a force. So Einstein said it is space-time curvature, but it is still a force. Let us try to unify it with other forces. So you are actually unifying apples with oranges. Space-time is a curvature while others are fields, and so maybe you shouldn't be doing that.
And As a layperson, one has heard about this Big Bang theory versus
Yes.
solid state. What could be?
Okay, there is only one person who believes in steady state, which is Jan Narlikar. Okay, and we constantly debate that. He was my PhD thesis advisor, so he still does. Some beliefs will not go away. So every time we meet, we discuss this, and if he is going to give the talk, he will certainly say that no, this Big Bang thing is still not. He is not convinced. But no, steady, not solid state, steady state. So what steady state says is that the universe today and universe yesterday has the same behavior, same phenomena. It doesn't change. It doesn't evolve, roughly speaking. This was the original steady state, but that was a very beautiful mathematical idea. This is what Fred Hoyle came up with. And then with just that symmetry, he could figure out how the universe should expand. And from how that is expanding, he could derive how Einstein's equations has to be modified, etc. The trouble was this cosmic microwave background radiation I told you. It tells you very clearly that I can see what the universe was when it was 1,000 times smaller, and it doesn't look like the universe today. So it was thrown out because of observation, not because of philosophical debates. But then, of course, 65, the observations were not too good, and then it slowly built up and built up and built up. At some stage, Jan, Burbridge, and Arp, they decided that steady state has to be abandoned, and they came up with a concept called quasi-steady state cosmology, which is a sort of halfway attempt to reconcile with the observation. But even that doesn't work very well. So I think Big Bang is the way to go. Yeah.
So in this theory which you have presented,
Right.
we used to expand whatever, there is no big crunch expected.
There is no big crunch. So with this, omega equals 1, it is like a stone thrown with escape velocity. It will expand forever.
So entropy will continue to what you call increase in the universe, and eventually we'll have what you call
Hit death, absolutely. That's correct. And we will,
that's prediction that is something made by theory which you have.
right. And it is actually worse than that. What is going to happen is that it is going to expand with accelerations. It is exponentially expanding. So very soon you will not be able to see light. You will be isolated.
That will be stretched also therefore? Are you saying the nucleus will be stretched also?
No. The expansion works only at the galactic scale, but you will see less and less number of galaxies because they are going to be rapidly separated from each other. We are a very lonely place in a few billion of years. Yeah.
So does the modern science of cosmology now preclude multiple universes?
By multiple universes, you mean the multiverse concept? Okay. So the multiverse concept, let me explain the context in it. The string theory has extraordinarily serious problem accounting for a positive cosmological constant. They work in what is known as an ADS space, and that has this cosmological constant with a wrong sign. So there were attempts and some very clever schemes were produced in order to come up with positive cosmological constant. It works mathematically, but it gives you a variety of values for the cosmological constant and other parameters. So an idea was put forward that there is not one universe, but there are several universes, and in each universe all these parameters, say mass of the proton, mass of the electron, any of these things can take any value, but only in certain universes the values will be conducive to human life. It is called anthropic principle, and only there we will be asking these questions. So the multiverse was required in order to save these ideas. But other than that, it had no observational evidence. And in fact, the other universes in the multiverse is something which you will never see. Yeah, they are causally disconnected with it. So we don't need that concept here.
Concept is now
It is not, it is redundant because I can explain the value of the parameters by this method.
Fluctuation, which you
Yeah, one second.
Now, at your disposal, there is a modern technology.
Yes.
And you say at 1990 cosmology started. But at the time of Mr. Einstein, there was no modern technology.
Yes,
And for cosmology, observation is essential.
right.
So how could he come up with so many theories which are still applicable?
Yes. Einstein made the biggest blunder because of this. What happened was Einstein wrote down in the back of a paper the equations which he has derived, and he derived that the universe is expanding. That would have been a great movement for human civilization, not just physics. For human civilization, if an individual can write a few equations, solve and say that the entire universe is expanding. Einstein got cold feet. He tinkered with his equations. introduced what I was telling you today, this cosmological constant, and found a steady state solution to that, where the universe is not expanding. Then observations came and showed the universe is expanding, and he said, oh, this is terrible and this is a blunder. And I mean, he didn't say cosmological constant was a blunder. That is how it is usually represented. What he said was, having missed predicting the expansion of the universe was a blunder. And he introduced the cosmology. And he actually made one more mistake. Even with cosmological constant, the universe expands. I mean, as I told you, it expands with acceleration. So that, in some sense, he made a bigger blunder at that. And it was immediately pointed out. De Sitter and a few others immediately caught that and said that, look, it will still expand. So without observations, when you speculate, even if you are Einstein, you can get it wrong.
This dark matter,
Yes.
some says a weakly interacting massive particle.
That is right, WIMPs.
Still made of this.
That is still the leading candidate. There is also something else called axion, but I would like to wait until it is seen in the laboratory. So there are huge efforts which are going on where they want to detect the dark matter particle in the laboratory. I believe it is possible. But it is just like when I talked about these perturbations in the cosmic microwave background radiation, this was predicted long back. Until 1992, it wasn't being seen. There were only bounds. And people who were skeptical were already started saying that, look, something is wrong, we are not seeing it, etc., etc. But then in 1992, it came. It's just a question of technology. So I believe it will be seen in the laboratory. Only when it is seen in the laboratory, we will really know what it is. The leading candidate is still WIMPs, weakly interacting massive particles. There is another candidate called axions, which is also good enough. But until we see it, we don't know.
So vacuum fluctuation, which you mentioned.
Right.
Suddenly you create an anti-particle nothing can annihilate.
Right.
And according to Stephen Hawking, at times it can go
Inside a black hole, and the other one will come. Yeah.
This is purely a theory, or is there an observation to actually?
Unfortunately, we do not have any observational evidence for the Hawking radiation because it is very tiny. But what people have done is again something very clever. There is something called analog gravity, which is like you replace the speed of light by speed of sound. That is, you take water waves and you have waves, and then you can create analogs of black holes in water, this thing. And there you can check whether there is Hawking radiation. And there are initial results which suggest that something like that is there. No, but there is no direct observation. Thank you.
Thanks a lot, Professor Padmanabhan. It was very interesting. Thanks a lot for a good gathering. Next month on 14th of March, that is Tuesday, Einstein Day. So that day we have a lecture of Dr. Jain Narlikar, The Lighter Side of Gravity. Kindly attend in a good number. Thank you.